Good morning, student. We'll start now. So in the last class, we have completed our unit number 2, which was based on image enhancement techniques. So in this way, we have completed 2 units from the syllabus. And if you see, we have four units which are main, and fifth one is more general, that is application in different domains. And in most of the universities, they will have 6 units, and they have color image processing and morphological processing or texture analysis as their 5th and 6th unit. So that's why if you see the question paper that I have shared with you yesterday, you can find the question from those units, that is color image processing and morphological processing. So if you see, let me show you some questions. So here we have explain the RGB and HSI model in brief. So this belongs to color image processing. This question elaborate the morphological algorithm for thinning. This belongs to morphological processing. This is second question paper. Here we have write short notes on hit and miss transform. So this is from morphological processing. Color models, it is from color image processing. Okay, so in each question paper you will find some out of syllabus questions. Okay, so if you get confused whether this question is from our syllabus or not, so you can post that question in our group. Okay, so anyone can answer whether it belongs to our syllabus or not. Okay, so let us start with third unit, image compression. So in this unit we are going to study different algorithms and standards which are used for image and video compression, and we are more interested in image compression. Now what is the need of compression? So consider one example. Consider we are recording a 2-hour standard definition movie. Okay, and we know that in standard definition we have this resolution. In HD we have, in HD movie we have resolution of 920 by 1080. Okay, so now we will calculate how many storage is required for recording this movie if we use 8 bits for 1 pixel. Now as this is color movie, we require 24 bits per pixel. Why 24? Because every pixel will have RGB value, right? So 8 multiplied by 3, that is 24 bits. Okay, so our array size will be 720 by 480 by 24, and most of the video recorders records at 30 fps, that is frame per seconds. So for every second, in every second they will record 30 frames. Okay, so what will be the data rate for these numbers? So it will be 30 into the dimension of each frame multiplied by 3 bytes per second. Okay, 3 bytes, 24 divided by 8, that is 3 bytes, not bits. Okay, bytes per second. So this is the data rate, and it is for 1 second. So for 2 hours, so it will be this much into 2 hours. So now this is the factor for converting hours to the seconds. Okay, so for 2 hours we require this much bytes or this much GB, 224 GB, and we know that the capacity of one DVD is 4.7 GB. So in order to record this movie we will require around 47 DVDs. Okay, so which is a huge quantity. Okay, so and we know that in our general DVD we have 3 to 4 movies. Okay, so see what is the factor by which we compress any video. Okay, so if we have 4 movies in one DVD, so the compression ratio is this one, 47 into 4. So we reduce the size of any recording by this much factor. So that's why the compression is very essential. Now, so what to study in this unit? So we are going to study fundamentals, where we'll study different terminologies and types of redundancies. So this is the redundancy is the cause. Okay, and if your data has redundancy, then the compression is possible. And then we are going to study general image compression model, then types of compression. So obviously it will be a lossless versus lossy compression. In some of the application, lossy compression is means possible, means it will be allowed, okay, and some application will not allow loss of information, so there we will use lossless compression. Then we'll see fundamentals of information theory, and then we are going to study different compression techniques. There we will study run length coding, Huffman coding. Under dictionary based coding we are going to study LZW. Finally we will study arithmetic coding, and finally we will study different standards like JPEG 2000 standards are there, that we will study. Now what is the objective of compression? So the objective is to reduce the amount of data required to represent an image. Okay, so to reduce the amount of data, and how it is possible to reduce the amount of data? Most of the images has redundant data. So if you consider this slide as an image, you can see a constant background like this, and most of the text is having the same intensity value. Okay, so images contain lots of redundant data, and if you are able to remove such redundant data, you will achieve compression. If you consider a video, the consecutive frames, they vary by some amount of information. If you consider this presentation as a video, if I don't move the mouse, the subsequent frames will be similar, right? They will be identical. Okay, so video are also having lots of redundant data. So if we remove that redundant data, we will achieve the compression. And if you see now, if you consider this region of this slide, and I can determine the intensity value of this pixel from its surrounding pixels. Okay, so can I say these pixels are spatially correlated, right? So if we transform 2D pixel array into the statistically uncorrelated data set, that process is known as a compression. Okay, so we will transform our array into the statistically uncorrelated data set. Okay, so that data set which is uncorrelated, there is no correlation between the neighbors. Okay, such process is known as a compression. Compressed image is reconstructed to get the original image or an approximation, and that process is known as a decompression. Okay, so if our compression algorithm is lossless, you will get the original image back. Okay, if you apply the reverse process. If our compression is lossy, then we will get the approximation. Here our aim is to save storage space and to reduce the transmission time. Now we will see the definition of data compression. It is a process of reducing the amount of data required to represent a given quantity of information while preserving as much information as possible. Okay, so here we want to reduce the amount of data to represent the given quantity of information. If you compare these two terms, data and information, these two terms are not synonyms. Okay, so if one student may write 10 lines of paragraph to convey some information, and some other student may write only 5 lines to convey same information. Okay, so here the data, so here we have only 50% of the data as compared to this image. Okay, but information that is conveyed is same. Okay, so that is the difference between data and information. Data is the means by which information is conveyed. Okay, so in both the examples or images, the information is same. Okay, but here we have this image requires less amount of data. It addresses the issue of data redundancy. Okay, so remember what is data and information. Data is the means by which information is conveyed. Image compression has numerous applications, starting from tele video conferencing to remote sensing, document imaging, medical imaging, fax, internets. Okay, the applications like document imaging and medical imaging requires lossless compression, whereas internet and multimedia application allows lossy compression. if you send one image via WhatsApp, you can see the size will get reduced, right? So multimedia applications allows lossy compressions. Now we'll see different terminologies. First one is known as a compression ratio, which is represented by CR, or some of the cases you may find only it is represented by C only. Now consider this is our original image or dataset 1, and it requires n1 bits for storage, and after compression the compressed image or a dataset 2, let's say it requires n2 bits. The ratio of this n1 by n2 is known as a compression ratio. Okay, so for example, if the image 1 requires 10 bits, and after compression if the compressed image requires 10 bits, so the compression will be compression ratio will be 10. Okay, so for the ideal compression you want the value of CR as high as possible. Okay, so this is compression ratio. Next terminology is known as a relative data redundancy. It is given by this equation. It is 1 minus 1 by CR. Okay, so if you put the values for our example, okay, so where the C was 10, so you will get, okay, so it will be 9 by 10, so 0.9. What is the meaning of this value? Relative data redundancy. This represents your data is having 90% of the redundant data. So this is the meaning of this value. Okay, so originally we had 100 bits, later after compression we achieved, means the compressed image was requiring 10 bits. Okay, so that means 90% bits are saved. Okay, and it represents this 90 bits were redundant data. Okay, so that is the meaning of this relative data redundancy. So here same example is given. If CR is 10 by 1, okay, you will get 0.9 as the relative data redundancy. That represents 90% of the data in the data set 1 is redundant. Now we will see different cases, and we will see which case is ideal for us. If n2 equals to n1, okay, so CR compression ratio will be 1 and relative data redundancy is 0. That means there was no redundant data. Then next one, if n2 is much smaller than n1, okay, so CR tends to infinity and RD is 1. That represents it is a significant compression and our original data was containing highly redundant data. And third one, if n2 is much greater than n1, in that case CR tends to 0 and RD will be minus infinity, and it is an undesirable case. Second data contains much more data than the original. Okay, so it will be a reverse to the compression. Okay, so the ideally we should get a case 2. Okay, n2 should be much less than n1. Now we will see different types of redundancy. So redundancy can be divided into two categories, that is statistical redundancy and psychovisual redundancy. Statistical can be further divided into interpixel and coding. Okay, so let us see these redundancies in details. Data compression is achieved when one or more these redundancies are reduced or eliminated. Okay, so the algorithms which we are going to study later on tries to reduce one or more these redundancies. Okay, one example I can give, Huffman coding. It tries to reduce the coding redundancy. Some other technique will be there which will try to reduce the combination of this redundancy. Okay, so in this way we are going to achieve the compression. Now we are going to study these three types of redundancy, that is psychovisual, coding and interpixel. Now what is code? It is a list of symbols, and with the combination of code we can create a code word. Okay, so here this is the example of code word. If you are representing any intensity value with 3 bits, Okay, so this represents one code word, and code word length means number of symbols. In this case, symbol is a bit. One symbol is a 1 bit. Number of symbols in each code word. Okay, so length is 3, symbols are 0 and 1, and we are using a binary code to represent the intensity value. Now assume that for a discrete random variable rk, in our case it will be a intensity value, and it will be in the interval 0 to L minus 1. So this L represents the intensity levels. So for the gray level, the value of L will be 256. Okay, represent the gray levels of an image, and each rk occurs with the probability of P of rk. So this is the probability of occurrence of intensity rk. So if consider one image where we have all the white pixels, then the probability of 255 intensity value is 1, right? Whereas probability of any other pixel will be 0, right? Okay, so in our image all the pixels were white pixels. Okay, so their intensity value will be 255, so their probability will be 1, probability of other intensity value will be 0. Okay, so that is the meaning of this probability. So it will be a ratio of nk, that means the number of occurrences of that intensity, divided by total pixels. Okay, so L is the number of gray levels, nk is the occurrence of kth gray level, it will be occurrence of rk, n is total number of pixels in an image. Okay, so if the size is m by n, so n will be equals to m into n. Okay, we have seen this equation when we have discussed histogram equalization. So we have found out the P of rk. Okay, then LRK represents number of bits used to represent each value of rk. How many bits are required? Okay, so till now we have used 8 bits. Okay, so the value of LRK will be 8. Then the average number of bits required to represent each pixel can be calculated using this equation. Okay, so for every intensity value you are calculating the number of bits into the probability, so it will be the average number of bits required to represent each pixel. Okay, so the total number of bits required to code m by n will be what? This is the average number of bits into the number of bits will give you the total number of bits, right? Okay, so the equation to calculate total number of bits required to code m by n image will be this one. Okay, now consider one example. This example will illustrate coding redundancy. Now this image is having only 4 intensity value. As you can see, this star is having 1 intensity value, this gray background is having 1 intensity value, this region is having 1 intensity value, and these lines are indicating 1 intensity value. Okay, so here we have only 4 intensity levels, and the probability of other intensity level is 0. Okay, as you can see, 128 means this star is having the 50% probability, then this dark region is having 0.25, then other is having 0.25, and the line is having 0.03 probability. Okay, this the size of this image is 256 by 256. Okay, now if you use our general code, so that means for every pixel if we denote the intensity level by 8 bits, okay, so code will be like this. Okay, LRK, L means what? Number of bits, so we are using 8 bits. Okay, then these are the codes obtained after applying Huffman coding. Okay, we are going to study Huffman coding in detail. Okay, consider these are the codes obtained after applying Huffman coding on this image. Okay, now as you can see, we are using 2 bits to represent this intensity level, then 1 bit to represent this 128 intensity, then 3 bits and 3 bits. Now let us calculate how many bits are required to represent the image which is using these codes. If a natural 8-bit binary code is used to represent its 4 possible intensity, then L average will be 8 bits, right? Obviously, every pixel is represented by 8 bits. L average, which is the average number of bits for code 1, will be 8, right? Because 8 bits for all RK. On the other hand, if the scheme designated as code 2 is used, then what will be the average length of encoded pixel? So it will be 0.25 into 2, so which will be this multiplied by how many bits required? 2. Then 0.47 into 1. Yes, okay. Then we have 0.25 into 3. Okay, one term is missed here, so it will be 0.25 into 3 plus 0.03 into 3. Now calculate. So now average bits is 1.81. Earlier we were required 8 bits per pixel. Now we are requiring 1.81 bits. Okay, so if you put the values in the compression ratio formula, so it will be 8 by 181. Okay, so which can be find out by this equation also. Okay, so 256 by 256 number of pixels multiplied by 8 bits per pixel, right? Divided by, this is the bits required. If you calculate by multiplying 87 into 2, then 128 into 1, like that. Okay, you will get this number. Okay, so compression ratio is 4.42 and the relative data redundancy is 0.774, and which indicates that data is having 77.4 redundant data. Okay, so this is the example of code redundancy. Unnecessary, we are using the number of bits, higher number of bits. Okay, so you can see coding redundancy is present when the code assigned to a set of events do not take full advantages of probability of the events. The probability of this star, that this intensity is more. Okay, so we can assign a less number of bits to that region. Okay, so this is the example of code redundancy. So with this example we can see that image was having 77% redundant data. Is it clear to you? Shall I revise this example? Okay, so second type is interpixel redundancy. So it is due to the correlation between the neighboring pixels in an image. We have seen, if you consider this region of this slide, okay, so we have high correlation between the neighboring pixels. Okay, so it is due to the correlation between the neighboring pixel. Okay, total information in this region is redundant. Any pixel value can be reasonably predicted by its neighbor. Now for that we are going to use this image. Again, this is computer generated image and its size is 256 by 256. As you can see, along one row we have a constant gray levels. Along one row we have constant gray levels, and the intensity value, they have equally likely probability. That's why if you plot the histogram of this image, you will get this flat curve. Every intensity level is equally probable. Okay, so we have 0 to 256 intensity values. Okay, they are equally likely. So observations are, all 256 intensities are equally probable. As you can see, the histogram of the image is uniform. Second observation is, because the intensity of each line was selected randomly, its pixels are independent of one another in vertical direction. Okay, so we have, so along with one line we have selected the same intensity, but the intensity along the vertical line are independent. Because the pixels along each lines are identical, they are maximally correlated. Okay, in the horizontal direction. These are the observation. Now for this, if you use run length coding, Okay, later we are going to study run length coding. Okay, I will explain this example. So we will require only 256 plus 256 into 10 bits. Earlier we required 256 into 256 into 8 bits. After applying run length coding, we will require only 256 plus 256 into 8. So this is the compression ratio that we can achieve. Okay, so this example is showing the interpixel redundancy. So what is the meaning of interpixel correlation? If I consider a two neighboring pixel, I can predict the value of this neighbor from the value of this pixel. Okay, so now, so if we just store the value of this pixel, and if required, I can determine the value of this pixel from its neighbor. Okay, so this is how we can remove the interpixel redundancy. So now what is run length coding? Consider this gray image, and this is the black and white image obtained after applying thresholding. Okay, now instead of storing all the intensity levels, what we are storing? We are storing only this run length. This is known as run length. So what is the meaning of these values? So for first 63 we are having, so this is the intensity profile of this line. Can you see this 100? This is the intensity profile of this 100th line, horizontal profile. So initially we have white pixels. Okay, then we enter in the black region here, as you can observe. Okay, there in the binary image we have only two intensity values, 0 and 1, right? So we will have black there. Then later we come to the white region, then we will have one intensity value. Then there is a spike, we enter into the black, and suddenly then we will come back to the white region, and then we have constant I think this is this line, this black line. Then we have constant black region, and then we have white region, and then later on again we have a black region. Okay, so how it is encoded using run length coding? So we have one intensity value for first 63 pixels, then we have 0 value for next 87 pixels, then we have 1 value for next 37 pixels, then we have 0 value for 5 pixels, then we have 1 for next 4 pixels, then we have 0 for next 556 pixels, then we have 1 value for next 62 pixels, and so on. Okay, so here we require 8 bits to store this value and 8 bits to store this value. Okay, so as you can see, for gray scale image we will require 343 into 1024 into 8 bits. For binary image we will require this much bits. For image which is encoded using run length coding, we will require this much bits. Okay, so using run length we can avoid interpixel redundancy. Okay, next, third type is known as a psychovisual redundancy, also known as a irrelevant information redundancy. Now, the human eye does not respond with the equal sensitivity to all the visual information. Okay, it is more sensitive to the low frequencies than the high frequency in the visual spectrum, and so discard the data that is perceptually insignificant. So this will be clear with one example. So consider this image. Again, this is computer generated image of size 256 by 256. Now if you observe this image, let me zoom, we can see only one color here. Actually we have intensity values for, I think as you can see from the histogram, so we have intensity values from 125 to 131, but we can see only one intensity value here. So our visual system is averaging those intensity value, and we are able to see only one color here. Okay, that's why we are saying Human eye does not respond with equal sensitivity to all the visual information. So here we can easily discard the other intensity value. We will keep only one intensity value which is highly probable. Okay, we can discard the other intensity values. Okay, it appears to be homogeneous field of gray. This image is appears to be homogeneous field of gray, can be represented by its average intensity alone, a single 8-bit value. The original 256 by 256 into 8-bit intensity is reduced to a single byte, and resulting compression will be, can you see this value, 65,000 is to 1. Okay, now this is the histogram equalized version of this image. As you can see, in the original image we have a constant region in the vertical direction and in the horizontal direction. After applying histogram equalization, that information is revealed. Okay, what we do in histogram equalization? So here we have a peak in the histogram of this original image, and in the histogram equalized image you will have a well spread histogram. Okay, so in that constant region, okay, so you will get a same intensity value. Okay, so that information was not visible to our human eye in the original image. Okay, so that is known as a psychovisual redundancy. So our visual system averages the intensity value and we cannot see the fine details. Okay, so that redundancy we can remove. Okay, so this is one example. So here we have 8-bit grayscale image. Okay, now here we have constant region. Okay, now we cannot see the fine details here. So instead of storing the image using 8 bits, we can store using 4 bit. And if you reduce, so we have seen the bit planes. So if you remove the lower significant 4 bit planes, okay, for every pixel you will require 4 bits only, right? And if you do that compression, you will get this image, and this is known as fall contours. As you can see here, we are getting a contours like means edge like structures here. Okay, that can be easily removed using IGS system. So what is IGS system? This image is also stored using 4 bits only, but false contours are not visible there. So how to achieve that? So what we do, so procedure is given here. We add the least significant 4 bits of the previous values of sum to the 8 bit of the current pixel. If the most significant 4 bit is 111, then we add 000. So see here, so we have ith pixel. Okay, consider we don't have this previous pixel. Okay, so that's why we have NA here. Initially the sum will be 000. Okay, then we add the 4 bits of the previous sum, so that is this one. Okay, we add this to the current gray level, and we store only significant bit, 4 significant bit. Keep only the most significant 4 bits. Okay, so the summation will be this one. We are adding 0, so the sum will remain the same, and we store only 4 significant bits. Then we add these 4 bits, a lower significant bits, to this gray level. We will obtain this sum, and we store only significant bits. Okay, higher significant bits. Then again we will add these 4 bits to the current intensity level, and we will store only the higher significant bits, and so on. Okay, so this is known as the IGS code. Okay, as you can see, those false contours can be easily removed. Okay, so we are adding actually a pseudo random number prior quantization. Okay, so this is regarding psychovisual redundancy. Okay, so we'll stop here. Any doubt? Shall I repeat any type of redundancy?